is that Louise wanted me to talk to you about these Boolean logic functions, these things that are being rewarded, and what it actually means for these organisms to have done these tasks. And then I can also tell you a little bit about what those rewards mean for the organisms and how they can use them to build up to other things. So we have to start out with the fact that computers in general are based on binary representations. We live in a largely analog world where we think about the fact that we can set things to what seems like an infinitely large number of possible states. But this is not the world that computers live in. Computers live in a binary world where something is either on or off, true or false. There is current flowing or there is not current flowing. And this sort of world means that we need to be able to represent things in binary states. So in Boolean logic, which is what these logic tasks we're talking about today are based on, the basic codings are either something is false or something is true. Now, if we extend that out to binary numbers, generally we'll consider false to be 0, true to be 1. When we move on to programming languages, for most languages, false is 0, and literally any other entry other than 0 is considered to be true, which means that things evaluate differently than a lot of people expect, because if you're used to the world of like binary numbers, you'd think true is always going to be 1. That's not the way most computers are going to interpret things. That can lead to problems with some of your programs. And with circuits, things are either off or on. This is why we get to binary representations in computer science, because computer science in many places is largely an outgrowth of an electrical engineering department moving into a new field. The places where it's not an outgrowth of electrical engineering and therefore not part of a college of engineering, it's an outgrowth of math when it's in the natural sciences. And then again, they tend to go to the binary number representation of everything. Now, this means that when we've got binary numbers, there are truth tables, which you probably saw at some point around Algebra 2, and quite likely have never seen again in the rest of your life, because if you're not doing computer science or formal logic in philosophy, these sorts of things don't really come up on a regular basis. So we're going to do a bit of a refresher course on what some of these Boolean representations even mean. So if I've got a particular statement, and here I'm referring to the statement as A, this is very standard sort of notation. Our first statement is A, it's either going to be false or it's going to be true. So we'll have zeros for every time something is false, and we'll have ones for every point that something is true. If I've got one statement, there's not a lot of logic I can do about it. It's either true or it's false, and I can deal with that. I can also take a negation of that, though. So instead of just A, I can also look at what is the value of not A. Now, this here is the most common representation of not, that we're going to have this sort of squared off line. You'll also occasionally see it as a tilde in certain other types of things. So if you see something that looks like this is the equivalent of not A. And people who are drawing it freehand will tend to do it this way. The people who put it into like formal write-ups, this is what mathematicians most often are going to use for that type of not. And the concept of not is that it's just completely the opposite of whatever the other statement was. That is, every time our previous statement was true, our not statement is going to be false. And every time our previous statement was false, the not of it is going to be true. So this gets us into A and not A, but we don't always rely on just one statement. We can also have a second statement. So here this is B, and so this is just going to be some other thing in its entirety. And this one also gets to have values of true or false, but those can be independent of what's going on with A. So instead of just having two rows here, where we've got one with false and one with true, now we're going to have four rows, because we could either have they're both false, we could have that A is false while B is true, we could have that A is true while B is false, and we could have that A and B are both true. Therefore, if we're completing out this table for not A, well, it needs to be the complete opposite of A. So everywhere A was false, not A has to be true. And everywhere that A was true, not A has to be false. We can do very much the same thing with not B. So rather than just me speaking constantly at you, what are our values here going to be when we try and fill out not B?
0, 0, 1, 1.
So you're saying that not B would be 0, 0, 1, 1. To me, that would be A.
I think I went too fast. So it should be 0, 1, 0, 1.
That to me looks just like B. I would say that our not B is going to be a 1 everywhere B is a 0, and a 0 everywhere B would be a 1. So our not B is actually going to be 1, 0, 1, 0.
That's why I don't do logic.
But you probably do, and maybe you just don't realize you're actually doing logic. The other advantage of us doing all of this online is that I have your names in front of me, so I can always call on people if I need to do that. Now, Kevin, you have the advantage that I actually know Jeremiah, and so I'm more likely to call on him in certain ways, which means I might intentionally call on you at some point later on. All right, so our not B is going to be just the complete opposite of what's going on here with B. Now we've got a bunch of different things that we can figure out patterns for. With logic functions, we have a few basic rules that we go off of. So one of them, this particular symbol here, this kind of looks like an A without the crossbar. This is going to be what we refer to as the AND symbol. So A and B logically is only going to be true if both A and B are true. That's kind of like saying, okay, so I've got one statement where I tell you that I'm currently wearing a red sweater, and I have another statement telling you that I speak English. Now, if I were to combine those together and say that I am wearing a red sweater and I speak English, that combined sentence is only true if both of the parts of it are true. If either part is false, or if they're both false, the overall statement is going to be false. So therefore, we need to look at the values of both A and B, and any place where they're both true, that's going to be true. And any place where even one of them is false, this thing is going to be false. So the only place these are both true are at the very bottom here, where we have A and B are both true, so we should have a 1 down here, and we should have a 0 everywhere else. So let's see if I'm right. And yes. So this is in fact the AND symbol. We get this at the very end. So we've got a bunch of zeros, and then we've got a 1. Our next logical symbol that actually matters pretty commonly, this is our OR symbol. The other way of combining things is to say that if either one of these statements is true, the overall thing is going to be true. So I could say that, either I am wearing a red sweater or I am speaking Portuguese. And right now, that statement is still true because I am wearing the sweater. It doesn't matter that I can't actually speak Portuguese. So here, we'd look for anywhere where at least one of the two of them is going to be true. So the only place it's going to be false is if both of these two things are false. And so that is going to be this top case here, where A and B are both false. That's going to result in a false OR statement. Everything else, at least half of that overall thing is true, so the combined statement is going to be true. So I come back over here, and you can see this is in fact just like what we were looking at. Now, with the fact that we've got 4 different values here. So we've got either both of the things are true, both of them are, both of them are true at the bottom, both of them are false at the top, and one or the other is true in the middle. We've really got 16 different patterns because we've got 4 rows. We've got 2 possibilities per row. Either it's a 0 or it's a 1. So there's 16 possible patterns here. And we can fill out lots and lots of different patterns here. We can go through them bit by bit. So one possibility is, let's look at B or not A. So that means we need to look at these two columns. We've got B and we've got not A. And if either one of these two things is true, we should get a 1. And if both of them are false, we should get a 0. So Kevin, I warned you I was going to call on you. Now I'm going to call on you. What is our value going to be for this column?
B or not A is going to be 1, 1. I lost my train of thought. So it's going to be 1, 1, 1. That's true in every case, isn't it? No, it's not true. It's not true in the third one.
It's not true in the third one. So that third one's going to be a
1, 1, 0, 1.
Yeah, so this is going to be a 1, 1, 0, 1. And so we can take a look at that. And that is, in fact, this combination here. We can go through and look even at, if I give you a set of numbers, we can look for what's going on here. So first thing to look at, we have 3 values here that are true and 1 value that's false. So that means that we're really fundamentally looking for an or statement where it's more likely to be true than an and statement where it's less likely to be true. You can see in our or statements, we've had 3 things being true. In our and statement, we only had 1 being true. So this one is going to be true except for this bottom case, which to me looks a lot like it's either not A or not B. In this case, I've got a true, a true, a true, and then a false. Again, this is way more detail about Boolean logic than any of your students will ever care about. The point here is to make you feel comfortable that this is something we do know and understand. Even if you can't regurgitate all of this later on, you can point people towards these are understood things, we can reference them. And that can be really helpful for students if they get tied down to like, what's going on here? You can redirect them that this is something we can know. Is this something you want to spend your time on rather than the science that we're getting to from the program? All right, so here we've got our not A or not B. And you can see we can write that this way, the not A or the not B. Now, instead of going through and showing you how we get to each one of these other ones off the bat, I can just show you, here we've got a bunch of the other patterns, all of the things you can get, and we've got different symbols for them. So we've got A or not B, which you can look at, it's either this first column or this fourth column. That's how we get the zeros lined up at the second row. Then here we've got not A and not B, and so on. We can go through and find where is the one place these things are both true. That's going to be here. So now I'm looking for these 2 things. So that's going to be not A and B, and so on. Now we get into a few slightly different symbols. So again, if you've never done formal Boolean logic, you will have never seen the symbol before. This is not a knock against you. This is people get really technical when they're drawing out symbols for things. This symbol here with kind of the plus sign between the parts of this circle, this here is the exclusive or. So normally when we say something is true with an or statement, it's okay if either one of them is true. With the exclusive or, we want one of the 2 to be true, but not both. So in this case, if both A and B are true, this is false. If neither A or B are true, it's false. But if one and only one of them is true, then it's true. That's a little more complicated. And then even more complicated than that at the computer science level, and we can explain why in a little bit later, comes the next one, which is the equals function. And on the equals function, we look for, is the value of A equal to the value of B? And to my human head, at least, the equals function seems like it should be simpler than the exclusive or, but the way we can actually build them using circuits, we require more wiring to get to the equals function than we do for the exclusive or. which is why in Evita, we're treating equals as the most complicated task, because mathematically it actually takes the most to build up to them. These last two options here, these don't actually require any input. This one is just the answer is always 0 or the answer is always 1. It doesn't matter what you give me as the input. Now, the reason why we're getting into all of these logic functions is this is what is being computed in Evita Ed. We have these various logic functions, and instead of working on one number at a time, they work on these very long numbers. They're 32-bit long numbers. And they compare both the 2 bits in the same position to each other and do one of these logic tasks on them. So for instance, in the OR function, we look for, is the output of that thing true at every step along the path it should be true? And is it false everywhere along the step it should be false for all 32 of those bits? And if they get it completely right, they get rewarded for you did the task correctly. If it's off by even one of them, they didn't actually do the task we were asking them to do. And I can get into more detail about that later. I just want to get through why we're even caring about this logic table right now. Now, great, these things have various symbols. These symbols look nothing like any of the symbols you see in Evita Ed. And you'll notice I said there are 16 patterns, but we only have 9 logic functions within Evita Ed. And there's actually a reason for that. So if we go through and look at these individual functions, well, we have to take into account the fact that we only have these 9 logic tasks. Well, some of these aren't actually different from each other, and some of them aren't even logic tasks. So if we look at the very start, A and B, we have, you are basically just repeating what you've been given. You're not doing any sort of computation. You're not doing any sort of comparison. You're just repeating back what we told you. And so if they get a number that's 11001 and the response is 11001, they didn't actually do any logic. They just repeated something back. This task is actually technically referred to as echo. There are times in the research version will require them to do this sort of thing. It can often be useful as a way to control how certain programs are operating. But this isn't really that interesting. It's very, very simplistic for them to do it. All they have to do is take in a number and then output exactly the same number. And so because it's so simple, it's not really that important. Similarly, these last two, where it's always 0 or always 1, they're not actually having to respond to the input values at all. That's just like, I am spitting out a string of zeros or I'm spitting out a string of 1s. So it's really trivial for them to do that. They don't have to rely on previous numbers they were given at all. And so these are fixed values, and these are all so trivial that we actually just discard all of these. All right, our next set of tests, here we have not A, and we also have not B. Now, from a logic standpoint, these two things are pretty much the same. One of them is we gave you a number and we asked you to give us the exact opposite of it. The other one is we gave you a different number and we asked you to give us the exact opposite of it. So these are both the same logic task. This is the logic task known as not. So when the organisms are doing that not task in Evita Ed, what they're doing is, I gave you a number that's like 00111, and they replied back 11000. It's the complete opposite of the number we gave them. And so they're doing some logic on it, but it's actually only a single input value. So this is the easiest of the tasks that we're doing. And now we can go into some of these other ones. These, if you remember, this red one here was the symbol for and. The green one was the symbol for or. These are the and task and the or task. So some things are relatively straightforward. Now I'm going to start removing some of these numbers once we've already identified what the task is, so we can look at just a smaller number of things and think about it in a little more depth. All right, so these two tasks that are in kind of this tealish color right now. Here we've got B or not A, and here we have A or not B. So in both cases, we have something or not something else. This is the or not task. This is the one that's listed as ORN because it's or not. And this is on your list of tasks within Avita Ed. These two, again, are equivalent. It's just which of those numbers are they looking at first? And the way Avita Ed works, we give them a whole bunch of numbers in the environment, and they have to output something that's based on the numbers they've been given. Those numbers don't really have a particular order to them in terms of which one do they have to look at first. They're just resources that are available within the environment. So these two tasks are equivalent. They're both the or not task. All right, so now we can look at these two tasks here in orange. We've got not A and B, and we have A and not B. So we could just rearrange this particular one here if we wanted to, that this one is currently listed as A and not B. We could list the same thing as not B, and you can see why I very rarely draw with this particular annotation tool if I'm trying to give letters, and A. Obviously, these two things are equivalent. And is a reversible command in Boolean logic. It doesn't matter the order in which you give it things. Similarly, we could treat this one as B and not A. You can see that these are equivalent statements. In either case, these things are what we end up referring to as the and not. We have something and not the other one. And so we've rearranged things this particular way. The reason why we choose to call this one and not is going to come up in just a moment. But for right now, I'm going to rearrange things and move everything we've talked about to the top row and move everything we haven't talked about to the bottom row, because that way we're looking at just the smaller set of things at the end. From here, we've got these 4 remaining tasks, and you can see we've already decomposed to, we've got 5 logic tasks and we've got 4 things remaining, and there are 9 logic tasks in Avita Ed. So none of these additional ones are going to combine together. Each one of these is its own task. So this purple one, we've got not A and not B. Now the way that not is distributed, this is actually exactly equivalent to not A or B. So if we took A or B earlier, if you remember, that was if it's A or it's B, we would have had one particular set of responses. And we started out with 0s at the top and 1s at the bottom for A and B. So it was only false at the very start when they were both false. The not of that is going to be the inverted one. We'll have things are going to here be true when both A and B are false. And they're going to be false where either A or B was true. So this is not or, which is nor. Similarly, here we've got not A or not B. So that's the same as not A and B. And so not and is the logic function referred to as NAND. And then the last two are ones that we've already specifically named. We've got this one with the plus symbol, that's the exclusive OR. The way this gets represented is the XOR. So that's the X for the exclusive, largely because putting EOR would be very confusing for people to be trying to pronounce. And then this last one is the A equals B, which is the EQU task. These are fundamentally the 9 Boolean functions that we work with within Avita Ed. The not function only requires a single number as input. All of the other functions require 2 numbers as input that we can get the right output for. Now these functions, here I've just arranged them in the order that we were talking about them. But as I mentioned, we can talk about things in terms of complexity of the circuit wiring required. And there are 2 basic logic circuits that we can build all of the other ones out of. Not is one of them. If you have a function that computes not, you can wire it back to itself or instances of itself that you can build up all of the other logic functions. The other one you can do that with, strangely enough, is the NAND function. So not and NAND are actually the simplest of the things to wire, and everything else takes more of them. So if we rearrange things in terms of the complexity, not and NAND are the most simple. They can each be done with just one of these circuits. And or not require 2 of the circuits, or and not require 3, nor an exclusive or both require at least 4, and the simplest way you can do equals requires at least 5 of them. Now, your Avita organisms are not doing things the most simple way they possibly could. They generally can with things like not. Everything else, they're evolving these functions. And evolution is not the most forward-thinking, efficient, or intelligently designed way to get about how things actually happen. Your actual organisms are doing far more complicated things that are very difficult to map out. But the advantage of working with this computational infrastructure is that we can actually just directly assess their phenotype. We're scoring, are you doing this function? That's our phenotypic assay. And it doesn't matter if we actually understand how they're getting to it from a genetic level. Now, as I said, all of these things are how the bitwise logic is being done, but this is being done on very large numbers. So if, for instance, you want to see my terrible attempt at drawing, despite the fact that we've already demonstrated, I really can't draw A's and B's all that well here. If, for instance, I have a number here of 1, 0, 0, 1, 1, I'm just haphazardly putting in ones or zeros. Because I'm a stickler for precision, I'm referring to this as haphazard rather than random because I don't actually have a random number generator process, and humans are not very good at doing things in truly random fashion. So this is a haphazard number rather than a random number. Jeremiah has heard me give talks before about student perceptions of randomness and knows I can go off about that for quite some time. Here I've got 2 different relatively short numbers. So these aren't 32 bits long, these are only 7 bits long. But if I wanted to do logic functions on these, I would compare each one of those. So for instance, if I wanted to look at the logic function that would be the correct result for and on these 2, it's only going to be true if both of the numbers are true. And it's going to be false literally everywhere else. So this number is the correct result of an AND function on these 2 input numbers. On the other hand, if I wanted to look at a different value, let's say I wanted to look at exclusive OR. So it's true if one and only one of these 2 input numbers was true, well, I'd get that true here, 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 and here. And both of these would be false. This one because both of them were true, this one because both of them were false. And so this here is the exclusive OR, whereas the one we had before, this was the AND function. What's going on in Avita is you get 32-bit long numbers, and it has to try and compute one of these logic functions on that. Now, when we said before that you can build up these logic functions from simpler beginnings, that's actually what's going on as evolution occurs. These simplest functions, things like NOT and NAND, are things that only require a relatively small number of genomic positions to be fixed in order for that to be the result of the organism. Anything further down is harder to get to. And the reality is that organisms have a hard time getting to these later tasks if they're not being rewarded for earlier ones. But they can co-opt the genomic positions that are doing these earlier tasks into building the larger ones later on. They've got looping structures within them, so they can say, loop together a couple of knots to get an AND. and then loop together some ands to get up to an and not or invert things. They build all of these more complicated functions by rewiring the earlier ones. And so it's actually really common for an organism to suddenly gain one of these tasks while at the same time losing one of the previous ones, because that previous one got co-opted as now part of the computation before it actually outputs a number. And so it has been absorbed into this higher function. But because the higher function is more valuable than the lower function is, there's still a net benefit to the organisms that do that. All right, so I've been babbling for quite some time about Boolean logic without asking you guys anything. So first thing I want to check in is this making any sense, and is this helping at all?
Yes. Yes to both questions.
All right.
I think it's helping a lot, yeah.
So what else would you guys like to hear about? Do you have questions about how things are working under the hood with the Vita Ed or with the research version? Do you want to know how it is we know that they're building these more complicated things out of the simpler ones? What would be helpful to you at this point?
Mike, I guess I'm curious how they build on one another. So how do you take the simpler functions and then build them on or make them more complex? That's I guess still pretty unclear to me.
All right, so I'm actually going to pull up our Vita Ed site and show you this on one of the sample organisms in there. All right, so we're going to start the Vita Ed site to launch this, and then I need to come back to Zoom and share my browser window. All right, so you can see I've got my virtual Petri dish here. I've got my freezer over here on the left. I've got my organisms here on the right. You can all see that? All right, so we're gonna come here to our organism viewer, and we're gonna look here at this all functions organism. So this organism comes preloaded into a Vita Ed, and this is one of the organisms that can actually do all of the tasks. And so I'm just going to move some windows around to make things a little easier to see. Now on this screen, you'll notice a couple of things here on this bar at the bottom. This bar is showing you the number of steps that this organism has executed. So it goes out to 430 before it reproduces. And we got these numbers here above the bar. So 3, 4, 0, 6, 5, 2, 7, 8, and 1. These are the genomic positions at which they output the final number that is one of these logic tasks. And the numbers here, the 0 through 8, correspond with these numbers 0 through 8 over here, which are those tasks. So it tells you at what point it's outputting an individual task. Now, if we go through, we can run the organism. We can also stop it wherever we feel like. You can see that this has started going through, and it's now in this looping structure. And this looping structure of this organism looks slightly different than the ancestral organism. The ancestral organism, it is looping over a much smaller part of its genome, and it's just using that to build the offspring. But here, it's looping over part of its genome where it's doing things other than just building an organism. There's computation going on here. One of the ways you can tell that is that these graphical representations here of the input buffer and the registers, these are changing. And you don't need to know the details of exactly what this means. These are graphical versions of binary numbers. So they have certain places they can store numbers. They have certain places they're taking in numbers. If it's yellow, it's currently a 1. If it's blue, it's a 0. So this is just the on-off thing. And if I'm running that, you can see that those buffers are changing because it's doing some computation. Now, if I want to, I can go back and look like here, it hasn't done any of the tasks. And here I get to the point where it's just done this particular task. And the point at which it's going to output something is actually always going to be this instruction here, Y. This is the IO instruction. IO is the input-output thing. So it takes in a number from the environment and it also outputs one of the numbers it was storing internally. And that's always going to be the last step before it gets rewarded, because now it's output a number. We check any number that it outputs to see, does that perfectly match the computation on one of the numbers it had taken in earlier. Now you can see this is just done task. This is just about to do task 3. And so that's now changed to look, it has performed that task 3. So it did this or not task, but the value that it output is still in the numbers that it has stored internally. So therefore, if it keeps doing computation on that set of numbers, it builds up to being able to do one of these more complicated tasks. And it does so by looping through the same structure of its genome. Does that help you at all, Jeremiah?
It does. That does make some sense. Thanks. So then I guess I would, by keeping, so 8 is the hardest one. So that means as you keep going through, you can't see my cursor, but as you keep going through, all of those, the other numbers that have been stored will then be used to help it do the equals function, right?
Yep. And
Okay.
it eventually builds up to doing that one. Now, oddly enough, in this organism, that's not the last one it outputs. It does a NAND after it's done all of the other ones. And it's true that when they're building up to do one of these more complicated ones, the more complicated ones tend to, on average, come out later than the simpler ones, which come out earlier. But it's not as strict, like it's not, the order here is not 0, 1, 2, 3, 4, all the way up to 8 every time. It depends to a certain extent on historical contingency. How did they build the code to let them do one of these functions? And how does that code interact either with itself or with other sections of the organism's code? Now, in this regard, when we're talking about how did they build up from the simplest functions to the most complicated of them, one of the papers that we'll talk about the most often here is this evolutionary origin of complex features paper. So that's this paper from Rich and Charles and several other people who you've probably heard of, including Rob. So this one's a Nature paper from 2003. One of the things they show in this paper is if you use the research version of VITA, and you can do this with the educational version, it's just going to take longer because it's a graphical user interface and it's not optimized to run on a high performance computing cluster. If you go into your environment and you set things up, you can choose whether you're rewarding all of the tasks or if you're only rewarding some of them. And so in this paper, they compared a bunch of runs where they only looked at the most difficult of these tasks being rewarded, and a bunch of runs where they included these simpler tasks as well. And they looked to see how many of the runs got an organism out to having these really complicated tasks at the end. And it turns out that in this paper, they show that if you reward the simpler tasks under the length of time they gave, under the mutation rate they had, under the particular random numbers they used, it happened pretty commonly if they gave them long enough. But if they didn't reward any of those simpler tasks, basically never. These organisms get to these complicated tasks because the simpler steps along the way are being rewarded. And so there's a selective pressure for those intermediate forms.
So it's almost like building a metabolic pathway.
It is a lot like building a metabolic pathway. And we actually explicitly make that connection within Avita Ed. Notice that these days, we're referring to this as the energy acquisition rate. So the rate at which they're getting resources because they've done these tasks they're being rewarded, we've coded all of these things as like and-ose and nanos as sugars. And then we are looking at how much does it cost them in order to make their offspring. So our fitness here is take the rate at which you're getting resources, divide by the cost of producing a new organism, and that gives you a rate at which you are producing new organisms, which is a measurement of fitness.
Mike, as I play with the Avita Ed, I often see the offspring cost also evolve. So what are they doing that changes that?
All right, so let's take a look at that. So in our ancestor function, you can see here, our ancestor is going to look a lot simpler than that evolved organism is. Notice that we just got a bunch of blank tape, but it's also only got an offspring cost of 189. And so this is a smaller organism in certain ways than the other one. Now, the total number of sites in the genome is fixed. Everything in Avita Ed has 50 sites in its genome, but they execute things in these loops. And in this initial one, if I'm running it, you can see it goes through, looks at these initial things, and then its loop is just this tiny fraction of the genome. And so it's not executing anywhere near as much stuff. If we have certain types of mutations, that can change how much of this is being executed. So we can change the length at which it's jumping back. We can also have mutations in here. So different mutations mean different things. These particular sites that are listed as C, these are no operation things. They don't actually do anything, but they can modify a neighboring instruction. So notice, for instance, as it's tracing out which of these things it's done, it doesn't actually come down on either this C or this A, because these things are modifying the instruction right before it. Similarly, this C is modifying the instruction right before it. So if I've got a mutation out here that changes one of these letters to something other than C, the C after it is now going to be modifying how it proceeds through that previous one. So that C is no longer executed. So it's going to take a different number of instructions for this new mutant to reproduce. Similarly, if I've got mutations here in this copy loop that tells it where to go back to, maybe it's going to go back further, or maybe it's going to go back not as far. And that's going to change how many sites are being executed in order to produce this new organism.
So is
Go ahead.
189 like the minimum then? Is that like the cheapest?
189 is not actually the minimum. This is the one we give it as a default, but right now it's building this new organism one instruction at a time. Each time it goes through the loop, it's only building one. Well, if we get a series of mutations into that copy loop that now instead of reading one thing at a time, it reads two things at a time and writes both of them, it doesn't have to go through that loop as often. So it can actually get smaller.
Thanks. That clears up some things I've been seeing as I play with the program.
So go ahead.
Mike, I guess I've got another question on kind of like maybe how the functions, how these organisms start, being able to perform the different functions. I've kind of been playing around with with a new version and trying to do something like a disruptive selection where you're having, two just extreme phenotypes. Mm-hmm. And when I was playing around with it, I looked at the functions, and I just picked not the NAND and the AND. I was going to try to play, I was playing around with those. And one thing I found was that the or not, or the number 3 function, ORN, seems to happen a lot faster than AND does.
So that is the thing that's true. In terms of like the minimum complexity required to do something, and or not are equivalent to each other. The reality is and gets lost a lot more often in a population than or not does. And most populations get to or not faster than they get to and. In terms of what is mathematically simplest, they're equivalent, but there's also a certain amount of contingency of it depends in part on what they start with. And everything in Evita has like, when we talked a little bit about, say, these registers and the stacks, there's a default location that any given number goes to unless it's been modified. That's what these C's and A's and B's are doing. A lot of them are modifying where numbers are going to or where numbers are being pulled from. By choosing to use C as our backbone, we have slightly biased the results. If we had used B as our backbone, a different set of tasks would be slightly easier and some of them would be slightly harder. And that's historical contingency of what our first ancestral organism is.
Thanks.
So the other thing I do want to take you back to, since you were asking a little bit about how we can build up some of these simpler tasks into some of the more complicated tasks, let's go back here for a moment to look at our logic tables again. So you can see we built to some of these more complicated ones of like, we got here up to the and not was one of these middle ones, right? Well, if you think about this, if we go back to our things, our and not is based on not one of these things and the other one. So if you start out and you've evolved a not function, you can go from A to not A, or you can go from B to not B. If you evolve an and function, you can look at the combination of A and B. You can then build to a and not by taking the not of one of those initial numbers and then anding it to the other number. And that's how we can get up to this more complicated function of and not by building together two of the simpler ones of not and and. Similarly, there are paths to all of the other ones. This is just a simpler one to explain quickly. Then here, let me explain to you how to get to equals using only nots, which is something you can do, but is not the most obvious thing if you're not used to thinking in these terms.
No, this helps. I don't think I understand the logic totally yet, but I'm starting to see the patterns and how this is working. This was really, really helpful. Thanks so much.
Well, good. And you'll have the recording of this. So if you ever want to go back and look at it later, it should be available to you. I am also available on email, although I will warn you, my current teaching schedule is ludicrous. So it might be a slightly longer time frame to reply to things